Hello everyone, my name is Peter Lyons and this is the lab number 2 for Physics 1 with Dr. Schatz, where we're going to examine the motion of a falling object. So in this lab I captured a video of the motion and then analyzed the video in Tracker to extract the object's position and corresponding time. I constructed a computational model based on physics principles that includes only the effect of gravity. Then I constructed another computational model based on physics principles that includes the effect of gravity and the effect of drag. I then compared my models and my observations by plotting the observed position versus time for my video, the predicted position versus time for my computational model without drag, and the predicted position versus time for my computational model in part C. Now in this lab, we're going to revisit Newton's second law, but observe an object's position over time on the y-axis instead of the x-axis. This introduces something that we didn't touch on in the previous lab, which is net force. After all was said and done, the results of this lab were that the laws of motion were upheld. Looking at our video and Tracker, here we see Yun, my friend, holding a ping pong ball at about head height. I have set the ping pong ball to be at the origin so that gravity would push it in the negative y direction. I have set a calibration stick to be 40 millimeters or 0.04 meters, which is the diameter of the ping pong ball. We press play, we can see that Yun drops the ball and it falls to the ground. Using these red diamonds to show the position of the ball at each frame, you can see that the positions get farther apart with each second, indicating a change in velocity, which can be confirmed by looking at this graph at the right, because there is a curve in the graph showing that there is a change in velocity. Now, the only other equation we need to worry about, other than the velocity and position equation for Newton's second law, is the equation for net force. The net force on an object is the sum of all forces acting upon said object. So the equation is F net equals F1 plus F2 plus however many other forces that it takes to account for all the forces acting upon the object. So in this case, we're only worrying about the object's weight and the resulting drag force, since the object is moving along the y-axis. Now I have, in my computer code, the ball.m, or the mass, set to 2.7 grams, or 0.0027 kilograms. The initial position is set as the origin, and the initial velocity is set to 0. In our calculation loop, you can see that the weight of the ball is the force of gravity, made negative, obviously, because it's going in the negative y direction, multiplied by the mass, multiplied by j hat, which is simply just a unit vector used to normalize the y-axis. Now for our drag force, we've got the drag force is set to be proportional to the square of the ball's velocity, with b being the proportionality constant. And so here we have right here F net equals the weight force plus the drag force. And then under that we have our typical Newton's second law equations for predicting the new velocity of the ball and the new position of the ball based on that velocity. Now, I have made two computer models, one including the drag force and another one not including the drag force. So let's run the one without the drag force. As you can see, there's a yellow arrow coming out of the ball showing the weight force, with a curved graph showing that there is a change of velocity over time. Running the code that includes the drag force, you can see that there is a yellow arrow showing the force of the weight, and then a blue arrow that changes with the velocity, which models the drag force. As you can see on the graph, it is still curved, but it gets to a point where it almost straightens out toward the end, showing that it might have gotten to a terminal velocity at this point. Taking all the data and all of our model from Tracker and putting it into Excel, we get this graph, with the blue diamonds being the Tracker data, the solid line being the model without drag, and the dashed line being the model with drag. And as you can see, that once we account for drag, the computer model fits the Tracker data almost perfectly. So, do any of the models predict a terminal velocity? Well, the model that neglects drag and only has the weight force does not predict the terminal velocity, simply because it has a constant force acting upon it and there's nothing that tries to cancel it out. But if you look at the velocity versus time for the model with drag, you can see that as time goes on, the velocity starts going toward a limit of around -4, and it's going to keep going and taper out at a certain point, which is where the drag force and the force due to gravity are equal to each other, which is where it hits its terminal velocity. Now, what if the ball is thrown downward? Would that mean that it would have a different terminal velocity, or no? Well, the answer is no, because every object has a respective terminal velocity, but it is not determined by the amount of force that it is thrown with. If you look at this block of code here that I have written specifically with a initial velocity of -3, so just imagining that it's been thrown, you can see that the line on this graph almost seems like it's a straight line, and so it just reaches its terminal velocity faster. Thank you very much for listening, and have a great day.